Okay, good morning. For those of you doing the International A-Level, here is last summer's Unit 6 exam. And for those of you doing linear Edexcel, this will be good practice for Paper 3, Linear Advanced 3. Okay, because these are the practical skills in physics. So whatever you've done in whichever syllabus that you've followed, the exams are examined differently. As you'll notice, the one in A-level, International A-level, is 80 minutes. And those doing linear, you have a 2.5-hour exam, and you still have a bit more time to get ready for yours. But this exam for Unit 6 International A-level students will be on Monday. That's their final exam, so I hope you found Unit 5 yesterday good. I noticed I hadn't done last summer's Unit 6 paper, so I've prepared a run-through for you to help you prepare, especially if you're one of my students. Okay, so this is last summer's exam, and we can go through it and see if there are any things which are new to you. Okay. You should really have done every single past paper already, so this will just be reiterating it if you've done so. I know some of my students have already been through this paper. Okay, so straight into it. The first question is talking about electrolytic capacitors. Okay, and I know for a start that we didn't stress the difference between electrolytic capacitors and non-electrolytic capacitors when we actually went through the content, which is in Unit 4 of the International A-Level, the first half of Year 13 for the linear students. So it also covers energy transfers in this equation. So there's a lot of theory which is also helpful for people doing the linear exam. This will help you prepare for your exam on Monday. I believe you have paper 2 on Monday. So an electrolytic capacitor obviously stores energy in the form of charge being polarized, and an electrolytic capacitor, you've got to make sure you got the polarity right, yeah? Whereas a non-electrolytic capacitor doesn't necessarily have a positive terminal and a negative terminal, okay? That's the main difference. So the student connected the capacitor into the circuit shown below. So usually we use a two-way switch, okay? So this side with the battery on it is for charging, and the other side is for discharging, yeah? And the discharging in this case is happening through the resistance of the motor. So when you're looking at the charging side, you want to have a look. The battery has polarity, so you've got to make sure the positive terminal, which is usually I think always the longer terminal of the capacitor. You can see this one is longer. That shows that it's the positive end. Same, the battery, the longer part of the symbol is the positive, and the shorter end is the negative. Okay? So, the question asks, state 2 safety precautions that the student should take when connecting and using. So when connecting and using the circuit. So connecting, ensure you connect the capacitor the right way around in terms of the polarity. Okay? That's what I just went through. So that's in when connecting. So this is the connecting part. Note the working potential difference of the capacitor, and make sure you don't exceed this value. All right. So this is when using it. Yes. You've got to make sure you don't go above the voltage that is designed for. Okay. There is a third point, which I've done in red as an alternative, and it's important for you to know this. So the third point, I'll do it in yellow actually because I've written it yet. Ensure the capacitor is fully discharged before handling it. because a large capacitor can store a large amount of charge, and this can actually give you a shock. Okay, so the capacitors store energy, and you can have a look at the formulae on the next page. So you have a formula sheet to see the equation for the energy stored in a capacitor. So these are the 2 marks. Any of these points will get you, 2 of these points will get you the 2 marks. So here we have the Unit 4 theory section, which went through further mechanics, fields, and part of fields. It's got the energy stored in a capacitor. So obviously the energy stored, for some reason they use W for energy stored, which doesn't really make sense to me. But anyway, so it's half CV squared. So if you know the capacitance and you know the voltage, you can work it out. Okay, and you can also work out, obviously, you can work out the amount of charge if you know the capacitance and the voltage. Okay, so it's basically it's electric potential energy that's stored in there. So continue with the questions. Now the practical side. The student used the switch in position 1 to charge the capacitor. The student changed the switch to position 2 to discharge the capacitor through the motor. A motor will have a specific resistance, presumably. So as the capacitor discharged, the motor then raised a small mass. So the output is potential energy. So they're doing the energy stored in the capacitor goes to lift the mass and give it gravitational potential energy. So it lifted it through a height h, and they want to ask about practical details. So you can see I put a set square here, I put a set square there, and I've clamped a meter rule to the bench. There's my clamp. Okay, so these are the things that they want you to do in the practical paper, whether you're preparing for Unit 6 International or you're preparing for the final paper in the 2-year course, the linear course. These are the skills they expect you to be able to verbalize. Okay, so the student used a meter rule to measure H. Here's H. Describe an accurate method to determine a single value of H, obviously using the meter ruler or a meter rule. So the key word, the operating term being accurate. They want you to know how to do things accurately, which my diagram has already shown you. So first thing is, in your language, you need to say clamp the ruler vertically close to the mass. You want it close so it makes it easier to read the exact height to the nearest millimeter. Okay? And then use a set square to ensure the meter rule is vertical, as shown. So that's set square 1. So these will get, set squares get you a lot of marks in A level. And then use another set square, the same set square, to ensure the height of the bottom of the mass, because that's where it's been raised from, the bottom, from the floor. Presumably it was on the floor initially, but not definitely, and is measured at right angles to the meter rule. So we want to make sure that this is an accurate method of determining how much to the nearest millimeter the mass has gained in height, so we can work out the potential energy. It's a describe, not an explain. Yes? So if they said explain, then you would need to note that the second set square reduces parallax errors. Yes, so this one reduces parallax errors. So I'm now going into teaching you about these things. Make sure you're at right angle to the instrument, and you're making sure that the meter rule is vertical. Otherwise, you'll have a systematic error. So this, the vertical that the meter rule needs to be vertical, otherwise it will give you a systematic error. And what does that mean? It means that you think you're measuring the height, but because if it's not vertical, it's actually measuring a component of the height. Yes, if you think about your trigonometry, if it's at an angle to the floor, so one is a systematic error, will give you wrong values, and the other is in unreliable values in that they are parallax errors. So parallax errors gives you unreliable data, and it could these are random errors that you could go either plus or minus by misreading it if you're not at eye level. The kind of things why you have the judges in tennis line judges are sitting at the line, across the line, perpendicular to the, so they can see the bounce of the ball properly. Okay? So you need to know the difference between random and systematic errors. Okay, the next part of the question, it says student repeated the measurements several times. The procedure. She recorded these following measurements, 4 of them, and they want you to calculate the mean value. So to get the mean value, you've obviously got to add them all up and divide by 4 and quote your answers to 3 decimal places. Why 3 decimal places? Because all the data is given to 3 decimal places, which is the nearest millimeter. Okay? The precision of your instrument is to the nearest millimeter. Yeah, the resolution of a ruler is to 1 millimeter. Okay, so you need to know things like resolution. Yeah, and they might ask it in the next bit. They then, in another part of the exam, so resolution is the smallest measure that you can make with that instrument. They then go on to ask you to determine the percentage uncertainty in the mean value that you calculated. Now the percentage uncertainty when you've got a range of data is half the range. Yeah, divided by the mean and multiplied by 100. I nearly forgot to do the multiply by 100 because they're asking for percentage uncertainty. Okay? So the range, if you look at the data, the largest is 0.246 and the smallest is 0.239. So that gives you a range of 0.007 or 7 millimeters. So that's 3.5 millimeters, half the range. So half the range divided by the mean, 0.242, multiplied by 100, gives you a value of 1.4%. And you don't ever want to quote percentage uncertainties to more than 1 decimal place, okay, or 2 significant figures. All right, next part of the question, they want you to determine the efficiency of the electric motor. Okay, so efficiency obviously is the useful output, which is gravitational, potential energy, divided by the energy input, which was the energy stored in the capacitor, which is the total input. So useful output against total input, and they've said efficiency. They haven't said percentage efficiency, so you can leave it as a decimal. Okay, so the mass of the that's being lifted is 0.02 kilograms. So you put these values into potential energy, mgh, yeah, using the mean height. So you get the output energy of 0.0475 joules, and the input using the formula that I gave you before, half CV squared, because we know the capacitance, given in microfarads. So you've got to change 10 to the minus 6, and you have the voltage of 6 given to you here. So you square that, and you get the total energy input of 0.0846. That means that the lifting of the load is 56% efficient, or 0.56 to 2 significant figures. Again, 2 significant figures maximum for efficiency. That's 11 marks. All right. So there's the mark scheme for question 1. Stop the video if you want to focus on any part of it. There's 1B onwards and 1C which is a total for question 1. Okay? Part B. Have I missed something here? Looks like I've missed something here, which means I can't finish the run through unless I have just put it the wrong way around. Part B looks like I've missed out the first part in the PDF. Yes, so part 2A is missing, and it goes straight into part 2B. So let's go into question 3, and then I'll have to go and find the master and rescan question 2. Part 3 is there, 3A. Yes, I think it looks like I've got, when I scanned it, it was single-sided and I put it the wrong way in the photocopier. Okay, so I'm going to go to question 3 next, which is, these are all practice questions anyway. So question 3 is a student investigated the rotational oscillations of a mass on a spring using the apparatus shown. So you can see that they're rotating it left and right, which is a variation of a oscillation. So the preliminary test would be to check how long it takes before it slows down. So how many periods can you count when you're oscillating it? So if you're doing this, it's always a good way to just check how long does it keep twisting, turning for. Okay? When the mass is displaced through a small angle, and you need a small angle, yeah, to reduce uncertainties and make sure the maths works properly. Okay, you always want to do things gently when you're talking about oscillations. The mass performs rotational oscillations about a vertical axis through the spring. Okay, so as shown in the diagram. The student uses a stopwatch to determine the time period. The stopwatch, the resolution would probably be 0.01 seconds. Yeah. Describe how the student should determine an accurate value for t. And that's why I'm saying, when you're trying it out, do a little preliminary test to see how many oscillations you can count before it slows down, or before it stops. So you need to time multiple periods and take a mean. That's 1 mark, okay? Maybe 2 marks. You need what they call a fiducial marker, which is a reference point. And for Edexcel, they always want to be the center of the oscillation, because obviously the oscillating system will always go through the center, but it won't always reach the amplitude that you started with as it slows down, okay? So this is a key point, yeah? Understanding fiducial markers for your exam. And that always gets you a mark. And the other thing that they like to do in A-level is allow the oscillations to settle. So you start the thing oscillating before you start timing. So you let it start oscillating, and then you start from when you're ready to get the timer to coincide with wherever you're starting your oscillations from. Okay. So those 3 points will get you, those 4 points will get you the 3 marks. You can have a look at the mark scheme. Hopefully I haven't photocopied it the wrong way around. The next part of the question says the student predicted that the relationship between the period and the mass was in this form. So they want you to take logs, because it's to the power b. Mass is to the power b. Well, if you take logs, and these are logs to the base 10, you should be able to take logs for year 13. It's not in year 12, but it's in year 13. Log of t will equal to log of a, plus the power goes in front of log of m. Okay? So this is in the form of y equals mx plus c, which I've done in red. So if you got t on the y-axis, and they want log m on the x-axis, then you know that the gradient is going to be b. So that's what they want you to explain. Explain how a log graph of t on the log t on the y-axis and log m on the x-axis can be used to determine the value of b. So b will be the gradient, and you've got to say that b will be the gradient, yeah, if you do that, and that will get you the marks. So they want you to show that you know how to look at y equals mx plus c in any equation they give you. So I've changed it to the y equals mx plus c form, and the intercept will be log of a, yeah? So that's the other thing you could determine, is the value of a, which is another constant in the original equation. So here the trick in the next part I will explain to you. The student measured or varied m, independent variable, determined corresponding values to t, so measured t, dependent variable, recorded her data m in kilograms, t in seconds, to a consistent number of decimal places. I think we need to start focusing on decimal places. The examiner tends to mention significant figures quite often, and in terms of measurements, you want it to be to the resolution of the instrument, okay, or the precision of your instrument, which is the resolution. They then want you to take logs, yeah, to plot a graph of log t against log m. So they've given you the additional columns for you to use your calculator to work out log to the base 10 of mass in kilograms and log of period in seconds. Now you can see what I've done is the correct notation for A level to follow. You've got to put both of these terms into the brackets because it's mass in kilograms. So you're taking mass in kilograms, you're not taking mass in grams. So you're logging mass in kilograms. So that's the notation. You've got to put both of them in the brackets, and time period in seconds. So once you do that, you also need to use this notation when you label the axes on your graph. Okay? And then when you do your calculations, you've got to give all values to a consistent number of decimal places. That's what I always tell students. Yeah, 3 decimal places with this data. Okay? They will accept 2 decimal places too, but you can see the first one has 3 decimal places, and then when you take the values, you'll have a look. We'll have a look at the examiner's done this data for me, so I don't need to do it. I just need to talk you through it. Okay? There are 6 marks for this section, yeah, to do the graph. And the graph includes these 2 columns here. Okay. They then want you to determine the gradient, obviously, as we said, to be able to work out B. And when on your graph, you should use a large triangle, show it clearly on your graph with the delta values of delta y and delta x. Yeah? So show your triangle, actually draw the triangle large on your graph. That will get you the mark each time. Then calculate M, yeah? And if you're within the examiner's range, in other words, you've plotted your data accurately, you will be in the examiner's range. And you quote to 2 or 3 significant figures for your final mark. Okay, so this is what you're going to do next, and I'm going to show you. And then after you've done that, they want you to then determine the value of A, and as I told you before, the log of A is the intercept on the log graph. The intercept on the y-axis, y equals mx plus c. And if you do that, you can follow my method. In a minute, you'll see that I've got a value of 3.43 for log. I've got 0.535 for the log of A. You then have to anti-log that, or inverse log it, or whatever the mathematical term is. And that means it's 10 to the power of 0.535 for those of you who know what logs are. So that'll give you the value here for the intercept. So we're kind of doing it in the wrong way around because I'm using the examiner's mark scheme to show you how to do your graph. Okay? And then you can give the unit, obviously, because you know the y-axis is in time. Okay? The intercept. So the value will be in seconds. because the equation that we did before, it's in time. Okay? So if the left-hand side is in seconds, the right-hand side must also be in seconds. But I think they won't penalize you for omitting the unit. So here's the mark scheme for the parts that we've already done. So part A, part B, and part B2, we haven't looked at the final part. So you see when they've done it, you see that what I'm talking about, the log must be with M and kilograms in brackets, T, capital, and S. And you'll see all the values are negative here. All the values here are negative. And that's because all the masses are less than 1. Yeah? Because 10 to the naught, yeah, is 1. And you've got less, 10 to the power of 1 will give you, anyway, anything less than 1 will give you a negative log, is what I'm trying to say. Okay? Whereas time, you're not less than 1, so they're going to give you positive logs. So your gradient is going to be with negative values on the y-axis. So you get 2 marks for your table if you've done the data correct. Okay? Consistent to 3 decimal places or 2 decimal places. This is the first time I've seen the examiners not mentioning significant figures and correctly going to decimal places. Okay? And then your axes must be labeled as I said. Yeah? With the brackets as I've explained. You've got to choose sensible scales. And we'll have a look at the sensible scales. That means multiples of 1, 2, or 5 only. Don't use any other numbers. Like don't go up in 3s, 4s, 6s, 7s, 8s, or 9s. And then the log values are plotted accurately and they will check. And if you have anything that's inaccurate, that means more than a small division out, you will lose the mark for sure. Okay? And then your line of best fit should be going in the middle of the points. That means you've got points above and below it. Okay. So this is the examiner's graph. Obviously it's a bit smaller than yours, but it's sufficient for this run through. So you see the labels I'm talking about, in brackets, log of time in seconds, period in seconds. So that's why the intercept is also going to be in seconds. Okay, that's the part of the question that we need to look at the end. Okay, so the gradient they used was from 0.485, what they determined it to be over here. Okay, that's what they read it off as. Difficult on this small graph, but that's what they're putting on. Presumably they had a big graph and in the mark scheme they made it smaller for the sake of their examiner's paperwork. And then you show your delta y here. So 0.485 minus the value at the bottom of the big triangle, 0.20. So there's your delta y value. And here's your delta x value, obviously from here. .1 is the bigger value, minus 0.1, I should say. Minus whatever the value is here, which they've determined to be minus 0.64. So this is how I want my students to do their graphs and their calculations. Okay? So again, the axes must be labeled with the notation for logs in the brackets for the quantity and the unit. Okay? Sensible scales I've been through, so you see their scales are going up in multiples of 5. Yes? 0.05, 0.10. So that's what I call multiples of 5. And they're going up in 0.1, 0.2. So 1s, 2s, or 5s. This will be in multiples of 1 or a factor of a tenth of 1. Accurate plotting we talked about, line of best fit. You can see that some of the points are below and some of the points are above the line. Below, above. You want equal numbers below and above. Okay, and that gets you your 6 marks. Then your gradient, calculation of the gradient using a large triangle. and the value must be in the range that the examiner thinks is a reasonable range to give students, and quoted without a unit to 2 or 3 significant figures. Yeah? So because I'm using the examiner's data, I get 0.53 to 2 significant figures, which I think is sufficient. So I didn't use the graph paper, but you should have. And you can see how many marks you think you get. You then read off the y-intercept for the final part of the question. Yeah? And convert it from the log value. So anti-log it, which the examiner's value gives you a value of the intercept 0.535. That means 10 to the power of 0.35 will be the value of A, and you can allow the units of seconds because we're talking about period. Yeah. But if you give an incorrect unit, you lose this 3rd mark. Okay. And there's your 17 marks for question 3. Question 4 is a student made measurements of the plastic protractor shown. Okay. The student used a micrometer screw gauge, full name, which has a resolution of 0.01 millimeters to measure the thickness of the plastic protractor. Yeah. And then here it says explain one technique. That means first state the technique and then explain the significance of it. She should use when measuring the thickness. Okay, well, you want to repeat your measurements with the micrometer in several different places. Okay, and calculate the mean thickness. That's always going to get you towards the mark scheme. Why do you do that? This will reduce the effect of random errors. Okay, so you do it in several places. It reduces random errors or things that could be either too big or too little. So that's what mean does. Taking an average in terms of a mean average. It does. And don't use the word average, you've got to use the term mean. Okay? Because obviously there are modes and medians too as an average. Okay, now you could also use this as your technique to eliminate systematic errors. You could check that there was no 0 error on the micrometer. Okay, and you can see the mark scheme has that as an alternative to your 2 points. So if you do random errors, you get 2 marks, but the explanation must fit your description. So repeat the measurements, take the average of the mean average. This will reduce the effect of random errors. Check the 0 errors. This will eliminate systematic errors. Okay. So remember, systematic errors gives you a wrong value, and random errors gives you an uncertain value. Okay. Next part of the question says, student determined the value of thickness as 1.41 millimeters. Explain why a micrometer screw gauge is an appropriate instrument. Well, your answer should include a calculation. That means they're giving you a hint. Don't just speak it, prove it. Okay, so the micrometer is an appropriate instrument because it has a resolution of 0.01 millimeters, which is the most accurate tool we have for measuring small distances. So the uncertainty will be half of the resolution, 0.005 millimeters. That's the standard procedure. So explain, you then go to this bit. So the percentage uncertainty for the value quoted above, which is 1.41 millimeter, will be half the resolution divided by the mean value times 100. And that will give you a small percentage uncertainty of 0.35%. So that's what they mean by including a calculation. Yeah, don't just speak about it, get some more detail. So detail, clarity, and depth is what gets you marks in any exam. So they then given you a diagram to show you the shape of the protractor. And you've got to determine the volume of the protractor. Okay? So this is the radius, half the diameter. Yeah. And obviously you could work out what there's a semicircular part to the protractor up to the dotted line. That's the semicircle. All right, then you've got an extra volume due to this thickness here and this thickness here, if you like. Is a rectangle. So you've got the rectangle area, green, and the volume of the rectangle is going to be x times the diameter times the thickness. And the volume for the semicircular bit will be pi r squared over 2, the area of the circle divided by 2, because it's a semicircle, semi means half, multiplied by the thickness. So we know the two equations, and then they've given us the data. And just to annoy you, they've given one in centimeters, this in millimeters, and this in millimeters with the uncertainty. Okay? I almost made a mistake of writing the uncertainty rather than the measurement for the thickness. Okay? So you know the total volume is going to be the volume of the rectangular part added to the volume of the semicircular part, okay, which is what my notation is showing. And you've got to show that the total volume is about 6.2 centimeters squared, to two significant figures, okay? So once again, here's the equation for the semicircular bit. So R, if you like, can go straight into it, or you can put d over 2. I've gone straight into R. And so it's pi r squared t, which is an area of a circle, divided by 2 to get a semicircle, volume of the semicircular part to 4 significant figures. I'm keeping the accurate value for the addition part, which is always what you should do. You keep your calculator value ready for adding. And then for the next part, the green part, the rectangular part in my diagram, is x dt, 0.45, x d. So I'm putting it in centimeters already because the answer they want is in centimeters cubed. So I forgot to say everything I'm doing is in centimeters cubed. So I'm changing the thickness into centimeters from millimeters. Okay? And I'm changing the millimeters here into centimeters. So these have been converted from millimeters to centimeters. So be careful you don't make a mistake. You then add those two values together to 4 significant figures. I've done it. It would be 6.244. To show the examiner, I know that I'm rounding up. Why am I rounding up? Because we want to show that to 2 significant figures. We have shown what is asked us to show. Now the next part is using the same data to show that the uncertainty in this value will be 0.2 centimeters cubed. So this is more difficult because the uncertainties are due to these values given here. So you could work out the percentage uncertainty of all 3 of them, yeah? And then for the percentage uncertainty of the semicircular part of the protractor, it's 2 lots of d because it's d squared coming into it. So percentage uncertainty of d times 2, so it's because d squared means there's 2 lots of d, so each one brings its own percentage uncertainty with it. You always add percentage uncertainties, for those of you who haven't been taught that. And then you have to add it to the percentage uncertainty of the other variable in the equation, which is t. So 2 lots of d, 1 lot of t, and pi and 2's don't have uncertainties. They're just numerical constants. So once you do that, you divide the value given for d of 0.05 divided by 10, the reading, 10.10, multiplied by 100, and there's 2 lots of those. 1 lot of thickness, 0.02 divided by 1.44. You don't have to have the same units now because it's just a ratio, and you will get 2 lots of 0.5, 1 lot of 1.4. Total maximum number of decimal places for uncertainties is 1 decimal place. 2.4 centimeters, or 2 significant figures maximum. You do the same for the uncertainty in the rectangular part. This time is no squared values, so it's percentage uncertainty of D, percentage uncertainty of X, and the percentage uncertainty of T. We did the T, we all know, is 1.4%. We know D is 0.5%, and you can likewise work out the percentage uncertainty of X by the values given. Here, it's 0.1 millimeter out of 4.5, so you can work out the uncertainties. When you add them up, it comes to 4.1%. So we now know the total percentage uncertainties of the two volumes. You've got to add the percentage uncertainties of the two values together. Yeah. And you to get the uncertainty, sorry, I'm not explaining it very well. The uncertainty of the total volume is the percentage uncertainty that we worked out for the semicircular part, which was 2.4%, multiplied by the actual value of each part. So this is the actual volume, because we know our uncertainty is the percentage uncertainty times the value, and this likewise the 4.1% for the uncertainty in the rectangular part, 4.1%, you multiply by the value we calculated in the part 1 above. So you multiply by that, and that was 0.64, and the volume of the semicircular bit was 5.61. So you got 2.4% uncertainty of the semicircular part, so 2.4% of 5.61, and you got 4.1% uncertainty of 0.64 to add. So you calculate each of the brackets. You get 0.135 for the first bracket, 0.026, and that gives you the total uncertainty of the two volumes. So this is the most complicated in terms of tediousness. It's mathematically obviously doable. You need to know how to do percentage uncertainties, and the more past papers you practice, the better. Okay? And that gives you a value of 0.2 centimeters cubed, one significant figure. Okay? And here's the mark scheme. Part A, A1 and A2. Pause the video if you wish to. Part B1, total volume calculated. See, they did pi d squared t over 8 because that's what happens. I just did a pi r squared t, yes, but it's the same algebraically. For B2, you either use my method, yeah, and here's their example of the calculation, or you use an alternative method, which I'll let you decipher in your own time, so we don't make the video too long. Okay, so there's an alternative method. You can see which way you've done it. I prefer my method. And then the final part of the question and the final part of the paper, unfortunately I had one page of question 2 missing. The student determined the density of the plastic as 1.04 grams per centimeter cubed with a percentage uncertainty of 3%. Okay, the accepted value of the density is 1.18 for perspex. So if you show the difference between the true value or the accepted value and the student's value, you can see whether the 3% covers it or not. That's basically what I'm doing. So explain whether the student's measurements suggest that the protractor would be made of perspex. Okay? Now, the percentage difference between the student's and true value is the difference in the values, 1.18 minus 1.04 divided by the true value. Yeah? And then multiply by 100. And you'll see the percentage difference gives you 11.9%, which suggests that it's much more than the experimental uncertainty of 3%. So either we've underestimated the percentage uncertainty, yes, or it's not made of perspex. So it's based on the data provided. It's unlikely, this data is unlikely to support the fact that it's made from the same material. It's not perspex. Yes? Yeah? Or you could conclude that the percentage uncertainty is underestimated. Okay. Now there's an alternative method in the mark scheme. You don't have to do it this way. I think this is the best way of doing it. So there they've worked out 3% will give you an upper value of 1.07 if you add the 3% onto it. Yes? So 1 plus 3% of 1.04 gives you this. Yeah? Or they do my method, which is 12% difference. Yeah? To me, this one makes more sense, but this one is just as valid. Okay? And then you compare the values and you get your 2 marks. I hope that makes sense to you. I will try to sort out question 2 once I find my masters and can rescan it. Okay, so if you find this useful, the exam is on Monday. If you're one of my students, make sure you know how to do percentage uncertainties. Go through all of them, and you can see this will be in the same playlist as all the other Unit 6 papers that I have done in previous months and years. Okay, so watch them all and do as many as you can over the weekend. And once you finish that, you are on physics, on summer holiday for physics. Okay, and if you want to keep in touch, you can keep in touch with me through YouTube, or you can contact me privately at an alternative time. Thanks for watching. Bye for now. Catch you in the next video.